Alright, amazing, welcome back. So with the foundation that we established in the previous couple of videos, it's time we introduced the Zio effects. So I'm not going to waste any time. I'm going to go back to our favorite project here under part 2, and I'm going to create a new Scala application. I'm going to call this Zio effects. Make it an object and with a main method for our little tests. Now, I'm going to introduce Zio effects by making the connections to the MyIO data type that we introduced a couple of videos ago. And I'm actually going to navigate back to the effects lesson that we wrote in the previous couple of videos, and I'm going to enhance the MyIO data type with a bunch of new features. So here I'm going to copy the case class. I'm going to navigate all the way down, and I'm going to introduce a simplified Zio effect. So I'm going to, first of all, paste this case class. I'm going to call this MyIO version 2, and I'm going to enhance it with a bunch of features. So here's the reasoning behind that. First of all, MyIO wraps a computation that takes no arguments and returns a value of type A. The first question, or rather the question that informs the next feature, is what guarantees the fact that this unsafe run may not throw any kind of exception? Now, in order to account for the fact that this unsafe run lambda may throw an exception or may result in a computation that might fail in some capacity, I'm going to first start to wrap this A value into a try. A try, as you well know, is a wrapper of a computation that might fail with an exception. Now, the try thing can only fail with a Java-lang throwable. And this is a very restrictive error channel. We would like to be able to encode anything that might mean something erroneous to us. Maybe an error code like an int or a string or any kind of domain-specific error. So instead of the try, we're going to use a different type. We're going to use either. And as you probably know from your previous Scala experience, either has two type arguments because either can have either a value of type A or a value of type B. And we consider the type B here on the right-hand side to be the quote-unquote desirable value, and the value on the left to be the undesirable value. So we can consider the left channel of either to be the quote-unquote error case, and the right channel of either to be the value case, or the desirable thing. So we're going to consider that this unsafe run will result in a computation that might either quote-unquote fail with an undesirable value E, which is why I'm going to add a type argument E here, or with a successful desirable value of type A. Now, in light of this expansion, it's worth modifying the map and flat map definitions. So I'm going to, first of all, call unsafe run on the original MyIO if I want to map it. So I'm going to say unsafe run, and I'm going to run a pattern match against it. And in case we get a left, which wraps some sort of error, I'm going to return that same error in the new MyIO. And in case we get a right with a value that I really want, then I'm going to run f, the function that we passed for map, on that value. So I'm going to have right with f of v. Now, notice that in this case, we need to change the type signature of map as well. So this is going to be a MyIO version 2 of type the same error type and B, and this is going to be a MyIO version 2 wrapped with this unsafe run. And similarly for flat map, we can say unsafe run. So I'm going to cut this out. I'm going to run a pattern match. And in case we get a left with some exception, quote-unquote exception, I'm going to return the same left value. And in case I get a right with a value that I'm really after, I'm going to call f on that value, and then I'm going to call unsafe run like this. Now, again, we need to change the type signatures. So this is going to be a function that takes an A and returns a MyIO with version 2 having the same error channel E and B. This is going to return a MyIO version 2 of E and B. And the constructor here is going to be a MyIO version 2, obviously with this new unsafe run method. So notice that MyIO version 2 also has an error channel now. And sometimes this error channel may be useful to recover from unintended consequences after running our effects, or maybe to retry our effects and so on and so forth. So this error channel is sometimes useful. Not only that, but our unsafe run lambda here can also be expanded. Right now it takes no arguments because we don't require any dependencies to run our IO effects, but what if we do? What if we actually require some sort of resources or environments to be able to run these myIOs? Which is why I'm going to add a third type argument to this myIO and require unsafe run to take an argument of type R. So unsafe run will now be of type R to either of type E and A. Naturally, we need to take the type signatures into account, so I'm going to add the type arguments everywhere, so REA, REB everywhere. And unsafe run now takes an argument of type R. So I'm not going to require a 0 lambda, I'm going to pass this little argument R, and I'm going to call unsafe run on this little thing. So I'm going to change the lambdas to reflect that. So I'm going to have R with unsafe run R and unsafe run R everywhere. Later in this course, we will understand where this R environment may be useful in evaluating this effect. And because this myIO data type is a little bit different than the IO that we started with, I'm actually going to refactor it. I'm going to call it myZio, because the Zio data type has a very similar signature to the case class that we defined here in very simplified terms. And one final thing that I'd like to add to this toy Zio data type is variance annotations, because the actual Zio library embraces variance, so it's useful to introduce this early. So the myZio data type, because it's a producer of values of type A, it's only natural that this Zio data type be covariant in the type argument A. Because this myZio can also fail with the error type E, thereby quote-unquote producing errors of type E, it's only natural that this Zio data type be covariant in the E data type as well. Now, because this Zio data type is covariant in E, notice that we now have this covariant type E occurs in contravariant position that we discussed in one of the previous videos, which is why we're going to solve it by introducing a new error type. I'm going to call this E1, which is a supertype of the original error channel E, and I'm going to consider that this new myZio will return an E1, and the final result is going to be an E1. Now, we understand that Zio is a producer of either the error type E or the value type A. What about the environment R? Because this unsafe run requires R, thereby consuming it, notice that we've passed it as an argument, this myZio is a consumer of the environment, which is why the R data type has a negative contravariance annotation for the R type. Because it's contravariant, again, we have one of those cryptic compiler errors saying contravariant type A occurs in covariant position, whatever. We're going to follow the similar solution that we discovered in the previous video, which is introduce a new type argument. I'm going to call this R1, which is a subtype of R. And I'm going to use R1 in both the argument and in the result type to make the compiler happy. But what is important is that this myZio toy effect is contravariant in the environment type and covariant in the error and value channels. Now, I spent a good few minutes, 8 or so minutes on my clock, to describe this toy Zio, not because I like to waste your time, because I don't take any detours, but because this model will greatly simplify the understanding of the actual Zio data type in the library. So without further ado, let's go back to the Zio effects lesson and let's describe some actual effects. So Zio has a big package that I'm going to import for pretty much all the rest of the lessons in this course. So I'm going to import Zio everything, and Zio everything for most intents and purposes will contain all the data types and all the functionalities that we need. So at the beginning of every lesson, we're going to import Zio everything. So let's describe our first Zio. I'm going to start obviously with a meaning of life. So meaning of life is going to be a Zio, and I'm going to start by describing a Zio that doesn't take any requirements. So I'm going to type the environment with any. It produces no errors, so the error channel is going to be nothing, and the value channel is going to be int, and I'm going to use a construct called Zio.succeed. So Zio.succeed with a value 42 will return a Zio effect whose environment is any, thereby requiring no effects. It doesn't fail, so the error channel is nothing, and the value channel is int. And if you're curious to see how the Zio data type is implemented, the trait Zio has the exact variance annotations that I described in the toy Zio that we discovered earlier. So this is how you can construct a successful event that's guaranteed to succeed. You can also construct a failed effect, so failure with Zio with any, let's say, string and nothing. So you know that just by looking at the signature of the Zio that this is a failure of type string, and you can say Zio.fail with something went wrong. You can also suspend the execution of another effect. Let's call this a suspended Zio as Zio.suspend with meaning of life. So you can pass another effect inside this Zio suspend construct, and the signature is going to be Zio with no required environment, so the environment is any. The error type is throwable because Zio suspend is used for those effects for which the construction itself may fail. So we have the error channel throwable, and the value channel is going to be int in this case. So this is how you can construct successes. So success, failure, and suspension, or the delay in construction of another effect. Now, Zios have map and flat map in the exact same style as we did for the other effect types. So let's call this improved meaning of life, MOL, as meaning of life dot map, and you can say underscore times 2 to double the value inside this effect. The error channel and the environment channel are going to stay the same in the type signature. You can also do flat map, so I'm going to say printing MOL as meaning of life dot flat map, and considering the MOL inside the effect, I'm going to say Zio succeed with print line the meaning of life. Now, because we have map and flat map, we also have for comprehensions. So I can say small program as a for comprehension by saying Zio.succeed, and I'm going to say print line what's your name. Then I'm going to try to read line, so I'm going to have my name as Zio.succeed, and I'm going to say std in dot read line. And then I'm going to print something, so I'm going to have Zio.succeed with print line, welcome to Zio, and I'm going to inject the name inside, and I'm going to yield unit. This small program has the exact same significance and the exact same mechanism as the I/O that we discovered in the previous videos. So that model is quite useful for us to speed up our understanding of Zio. Naturally, all of these Zios are being constructed, but nothing is actually produced unless we evaluate them. So if I try to run this application, nothing will get printed to the console, nothing will be evaluated until we evaluate one of these Zio effects. Now, besides map and flat map, Zio has a lot of combinators and transformers. And we're going to discover all of them, or most of them, throughout the rest of this course. There's no time in one single lesson to discover them all. They're all used for different purposes. For instance, a combinator that's quite useful is zip. So if I define some kind of Zio with integer, so I'm going to say another MOL as Zio.succeed with the value 100, you can zip these two together by saying tupled Zio as meaning of life dot zip with another MOL. And this will return a Zio naturally of a tuple int and int. You can tuple any two value types that you like. Of course, there's also zip with, which will allow you to pass kind of a lambda to process these two values and return some other value as a result. And you can say val, let's call this combined Zio as meaning of life dot zip with, and we're going to use another MOL, and I'm going to use, say, underscore times underscore to return another int. So this will be a Zio where the value type is another int combined by multiplying the two values from the Zios. Now I'm going to go straight for some exercises, not until I've discussed the type aliases of Zios, because Zio has 3 type arguments, and therefore it's quite natural to not want to write all these type signatures manually all the time. So it's worth simplifying some of these ZIO type signatures. First of all is UIO, a universal IO that cannot fail. So this is alias for ZIO with any, that is no required environment, nothing, that is it cannot fail, and this returns the value type A. So UIO of A is a ZIO of any nothing A. No requirements, cannot fail, produces A. So I'm going to have a UIO as UIO of type int, for instance, and the proper expression is to say ZIO.succeed with some kind of value like 99. The second most common type alias is called task. Task of type A is a ZIO that can fail with a throwable. So any throwable and A. That is no requirements, can fail with a throwable, produces A. So I can define a successful task as a task int, and an appropriate expression for a successful task is of course ZIO_succeed as well. So I can say ZIO_succeed with 89. And notice that because we embrace variance, ZIO_succeed, because it has nothing as the error channel, it's appropriate for a type substitution for a task. Similarly, I can say a failed task as, again, task with int. I can run ZIO.fail with some kind of exception. So I'm going to say runtime exception something bad. Again, because of variance, this is a proper substitute for a task of int. We also have a type alias that's called simply IO with the error channel E and A. So notice that this has two type arguments, and this is the same as ZIO with no requirements, can fail with E, and can succeed with A. So simply no requirements. This is very similar to the myIO data type with an exposed error channel. So I'm going to have a successful IO as an IO, let's say, of string and int. Because it's a success, I can also use ZIO_succeed. So I can say ZIO_succeed with 34. And I can also define a failed IO as an IO of string and int as ZIO.fail with something bad happened. So notice that ZIO_succeed and ZIO_fail are appropriate expressions for both successes and failures for a variety of tasks. And less used are those type aliases which require some environments. One is called URIO, which requires some environment and cannot fail, and it produces some kind of value. So URIO with R and A is the same as ZIO with R, nothing, and A. That is, cannot fail, but it can have some requirements. So I can define a URIO as URIO with, let's say, int and int, and I can use ZIO.succeed with, let's say, another kind of value, 67. Now, in order to actually evaluate this IO, you will need to pass in this requirement, and we're going to discuss requirements, environments, and layers a little bit later in this course. Now, because throwables are so pervasive in the JVM world, ZIO also has a type alias that's called RIO, with, again, an R and an A, and this is the same as a ZIO, which requires an environment, can fail with a throwable, and produces an A. And this can fail with a throwable. So I can demonstrate that an RIO as RIO with int and int. Again, I can say ZIO.succeed with some kind of value like 98, or you can also use a failure. So I can say a failed RIO as RIO with int and int, a RIO, as a ZIO.fail with some kind of exception, new runtime exception, RIO failed. So these are the type aliases of ZIOs. Now, for the duration of the course, we're probably going to use mostly UIOs and tasks. Now, you can keep this code or you can take a look at the repository as kind of like a cheat sheet of the type aliases that Zio offers. I'm pretty sure that by the time we end this course, you'll remember all these type aliases by heart, not necessarily because you'll do a giant effort memorizing them, but because we're going to practice the crap out of them. So let us start that little practice in the next video.